And we're back. Welcome back and happy Thursday. Today we're going to switch gears and look at the material for Chapter 2 concerning itself with operating system structures. That is the interface, be that to the human or to the application that the operating system presents in order to use its services. Before we begin, let's go through a few administrative bits. So the reading has changed. In the main text, OS concepts, sections 2.1 through 2.3, pages 55 through 74. Please get that done by a week from today on the 17th, which is a Thursday. Also, on the Blackboard, your required reading consists of a C Programming Essentials video, as well as a C programming tutorial document. We will be going over some C programming as it will be necessary to give you project work where you have access to the underlying details of the operating system. So at this juncture in the curriculum, you've all had data structures and algorithms too. You are all comfortable programming in Python, and as growing professionals, part of the name of the game is picking up new languages, and so that will certainly be the case in this class. Please make sure you do not fall behind in your reading. So let's begin with a little bit of a sidebar about memory and pointers. Now, we've talked about it a little bit, but we haven't said too much in detail, and this is going to be a sidebar about how pointers and memory are handled in the C programming language. And so let's imagine now we have our main memory. I'm going to draw it really, really big. And this main memory stores bits and bytes. And let's assume that we have a byte here, which is 8 bits, a byte here, a byte here, a byte here, here. And I'm going to draw a couple of them. I'll draw a total of 8 bytes. Now, of course, each byte is going to reside at some location in memory, and these locations are numbered, and each number is the so-called memory address. Okay, so let's say this is at memory location or memory address 1. This byte is at memory address 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, and so each memory location is associated with a memory address. And what a pointer is in C, it's a special type of variable that you can use to access memory locations using their address. So in C, unlike Python, in C you have to define the types for your variables and your data. Let's take, for example, UCHAR, UCHAR, some variable name A is equal to the character, let's call it Q. Now, if I do that, well, UCHAR stands for unsigned char. And what I'm doing here is taking this ASCII code, if you will, and assigning it to variable A. I could also say unsigned character A is equal to the number 8. Okay, so when I do that, what happens in the compiler? Well, the compiler takes this code and it, on its own, figures out where to store this thing in memory. So I have some variable named A, and A refers to some piece of memory, and let's say A is going to refer to this piece of memory, and that piece of memory just happens to be at address 11, and inside of that memory location, I'm going to store, say, for example, the value 8. Now, there's a variable type called a pointer, and in C, how I describe a pointer or declare a pointer, because in C you have to explicitly define all of the types of your variable. I say ucar star, and what that star means pointer to. So I'm going to define a variable, and that variable is going to be a pointer to a ucar. So let's say variable pointer. Okay. Now ucar variable pointer, it is called a pointer variable. It's called a pointer variable. And like any variable, it can store a value. So here, if I said ucar star var pointer, well, the compiler would allocate var pointer and associate that with a memory location. And that memory location, doesn't matter what that memory location is for this conversation, it's going to hold a value. So var pointer is a special type of variable. This particular type of variable is going to store memory location. That's what this pointer to, this star notation tells me. So if I want to actually say, okay, well, I want to store a memory location, an address, in this var pointer, this pointer variable, and it's going to be the memory location specifically of that unsigned character A. So I would say var pointer is equal to ampersand. That ampersand means address of. Address meaning the memory address. So var pointer is going to be assigned the address of whatever that variable A was. So what happens when I execute this line? Okay, well, it says, oh, var pointer. Var pointer is here, so it's going to refer to that location for that variable var pointer, and it's going to store in it the address of whatever variable A was. Well, the address of A here is 11, so it's going to put in an 11 in var pointer. So that var pointer, if I were to print it, you get the value 11, or the memory location or memory address associated with that variable A. So now, one of the beautiful parts about pointers is that you can now use this pointer variable to access memory. And how do I do that? Well, you use what's called arrow notation. I say var pointer dereference, that's our arrow notation. You say dash and greater than. Dereference, that's structures. You say var pointer star, that's the other type of dereference. I'm thinking about structures, is equal to, say, value 12. So what does that do? That var pointer, when I use this star notation, I'm saying take whatever that pointer variable was, go to the memory location that's stored in that pointer variable, and now assign to that this 12. That's also called dereferencing a pointer. Or sometimes it's called indirect addressing. And so essentially what I'm doing, I'm not accessing this memory location directly. I'm using the contents of var pointer, treating it as a memory address, and saying access whatever is at the memory address stored in this var pointer. Okay, and so the neat part about this is that if I have another variable, ucar b equals 7, for example, I can just set my var pointer to the address of whatever B is, and then access or dereference that var pointer and assign it a value like 20. If I do that, well, what will happen? Let's say B is stored in memory address 5. When I said var pointer is equal to the address of B, I wrote in 5, which is the memory address of B. I dereferenced it, so now B is going to get the value 20. And so this idea of a pointer is nothing more than a special kind of variable. It's a variable that stores memory addresses, and you can use that memory address storing variable to access memory or to change that memory. You can read it or write it. I could also, once I set it equal to the address of B and set it equal to 20, I could just print out what is at the memory location for that address 20. Okay. And so this idea of pointers and the layout of memory is one of the more sophisticated concepts you will need to learn based on your experience with something like Python. Languages like Python and Java were intended to be quote unquote safe. They were hiding the underlying details of the system from you and also protecting you from accessing parts of the machine that your program doesn't have or shouldn't have access to. The difference then in something like C and C++, they give you full access to the underlying machine and assume that if you are accessing some part of the machine, you must have a pretty good reason for doing that, so it lets you. Okay, so that's just a little sidebar on pointers. Please make sure, because we will pick up with much more detail about this in the next 2, maybe 3 modules. So please make sure you're looking at the other reading, both for C tutorial, the video, which is a great place to start, as well as the tutorial documentation. Okay, so the objective for chapter 2 is to describe the general services that an operating system makes available to everyone that uses it, processes that are running, users, as well as other systems it might be interacting with. So we'll look at all the different ways of structuring an operating system and explain also how they're customized, how they first start up or boot, and how they're installed. So let's take a look at system services. And operating systems give you an environment that allows you to execute programs, and it provides services or resources to those programs running, as well as the users that interact with the operating system, with the underlying machine. And so one set of operating systems, called the user interface, provides the user the ability to input commands to the system. And there are different types of human interfaces. One is called the command line, which is very basic. Another is a graphical user interface, which you're used to with menus and buttons and desktop. And the other is so-called batch user interface, and that's no longer very popular. But in batch interface, you would submit your program to the system would accept it and churn away, perform the running of your program, and you get back a printout with the results of your computation. A service offered by the operating system also includes, and this is very important, program execution. Your system has to be able to load your program from storage into memory and to initiate a process or thread and start the instruction stream, the set of instructions your program, trafficking back and forth in data between memory and the instruction and data cache, and either exit both normally, or if there's some catastrophic error, it exits abnormally. Your operating system also, as we discussed, provides I/O operations, that is, sending data off the computer or getting data onto the computer through some device. Now, this might be files, it might be network card, it might be to the screen, it might be a whole host of other devices that you have connected to your system. Operating system services include things like file system. We talked about storage and the logical presentation that the operating system makes for the underlying sectors on the platters and tracks of your disk. So The operating system has to decide where to put things, how close to put things, when it's chaining together a linked list of these sectors, giving you the illusion that a file is a contiguous tape of information in one contiguous sequence. It also includes services for naming them, creating them, searching them, as well as managing permissions, who can access, who can read, who can write these files. An operating system also provides for communication facilities, the exchange of messages between computers or through subs, be they on the same network or across a wide area network. And so communications can happen between processes as well. In that case, it uses memory through which to pass information between communicating processes, or it can be between machines, and therefore it's using the network card to do that. An operating system also provides error detection. When does some application violate rules imposed by the operating system? And these errors can occur in a number of places: in the CPU, in memory, on the I/O devices, or generally in the programs. One program might try to overwrite the data of another program. Now, for different types of errors, the operating system should take different actions to try to correct or eliminate the problem. There are also is support for debugging, the crafting of programs, and operating systems provide facilities that allow you or facilitate your efficient use and error-free use of the system. An operating system performs generally also resource allocation. If you have multiple tasks that run at the same time, how do you coordinate among them so that you keep the system busy and you also make efficient use of these resources? No one task can hog all the resources, yet they all should make some notion or semblance of progress towards what it is they're trying to compute. Operating systems also keep accounting, they keep tabs on how much of each resource each task or each user is consuming. Because in some operating systems, you share these resources, and it's good to know how much of each resource is being used by each program. Operating systems also provide protection and security. Now, this protection is the keeping apart of all of these users and processes so that they don't walk all over one another. They don't steal resources from one another. They don't write over data of one another. And so an operating system must keep processes and threads separate from one another, and it controls the access to system resources so that there's orderly sending of data and orderly reception of data. An operating system also provides facilities for security, for protecting resources from notional outsiders, be they outsiders in terms of users on a machine or users that are on different machines who might try to access things they should not be accessing. So let's take a view of an operating system and this is in the book. At the bottom, we have the hardware, and then right above the hardware is the operating system, and the operating system provides interfaces that shares the resources of the underlying hardware. And so oftentimes when you read the literature, you'll see something called the HAL. HAL stands for hardware, abstraction, layer. And that's just a masking over all the low-level details of the hardware to make it easier to interface and share those resources to the applications above. Now, made available by the operating system are so-called operating system services. And these services are higher-level libraries of functions, and these functions provide all of the operating system-like mechanisms that allow applications to use the shared resources of the system. And this is where all the accounting and protection happens. Things like executing programs, things like sending data to or getting data from the device buffer for an I/O device, things like the file system layout and management, things like the communication, allocating of resources, the taking of this accounting information, and the error detection, along with protection and security. And so all of these services are the runtime implementations of what it means to execute a file. So when you execute a program or a file, we said in a previous module that we need the program to be in memory, and we have the state or context associated with all of the components of the CPU needed to execute an instruction stream. And so as you're executing those instructions, the program execution component includes those data structures that represent the save state of a program that's currently executing its instruction streams. We also have these system calls. These system calls are an API layer, and this API layer uses these operating system services to make available a library of functions that allow applications to perform the operations implemented by these services. On top of the system calls, that's the user interface. That's the user's entry point into doing something on the system. So this is where the user comes into play. Now, these user interfaces can be simple, like the command line. They can be very complex and visual, like a graphical user interface or GUI. And then on top of that, you have other system programs and the user programs. This is where things like Microsoft Word or Firefox browser might reside. Okay, so we have this entire stack, and the relationship is at the seams between these various components. And so the operating system itself is the orchestrator, effectively, of all of the underlying hardware resources. The services, which is the main takeaway here, are the runtime implementation of how this underlying hardware is used in order for ultimately applications to make productive use of the resources on the system. So let's take a look at the system interface. Now, the first is the command line interpreter, and the CLI, or command line interpreter, is very simple. It allows you to directly execute a command, and sometimes this command is implemented directly in the kernel, sometimes it's by a systems program. It's a simple program that makes calls to the kernel for some purpose. And this command line interpreter is often called a shell, and there are different types of shells that exhibit certain types of behavior. Now, what this command line interpreter does, it gets a text command from the user, it executes it, and it prints out the result of that command on the screen. So it's that way for the user to interact with the system to get it to do something. So a popular command line shell is the so-called Bourne shell, right? Now, this is at the command line, and this is an example of the Bourne shell, specifically on Mac OS. And what I'm going to do is exit the PowerPoint momentarily and show you shell inside of a virtual machine for the Ubuntu Linux operating system. So here I'm running a virtual machine, and we'll talk about this in detail. This is the Linux operating system. Let me log in, and you'll see when I log in, it takes a second or two. Oops, let's see. There we go. So you can see when I log in, I have a graphical desktop, and I'm going to run a terminal, which is an instance of this command line interface that I was talking about. So let me move this window down. You'll notice a window pops up. It's a little bit slow. And in this window, if I can make it a little bit bigger, we can see a command line interface. Now, this particular command line interface, or shell, it's used to accept commands from the keyboard that you type in. And so here, I'm going to type PWD. PWD stands for Present Working Directory. When I hit Enter, the command line interpreter is going to get that command, execute a system call in the operating system, and return back the result. So I'm going to hit Enter. You'll notice it says I'm in the home directory in the operating system's concept account name. And so this command line interpreter, this particular one is for Ubuntu, and you use that to issue commands to execute system services that do something for you. Another one I can execute is ls, for a listing, and it shows me all of the files in my current directory. And that's the result of typing ls. So let me switch back to the PowerPoint. So we're back to the PowerPoint. Let's continue on. The command line interpreter or command shell is used to execute commands on the OS. A more friendly interface for the user is the graphical user interface, which you're all very used to. And sometimes it's called the wimpy interface. Wimpy or WIMP stands for Windows Menu Icon Pointer. The so-called WIMP, Windows Icon Menu Pointer. Now, in this case, when I say pointer, I mean the mouse pointer. And so a WIMP interface has all of these components: windows, icons, menus, and pointers. And it's the friendly desktop metaphor that you're all used to. So you have a mouse, a keyboard, and a monitor, and the icons represent things like files, programs, actions that you take, and various mouse buttons. When you bring them over objects, certain events occur, like you see information, or if you click, you can launch a program, get it to execute, or you can examine the contents of a file. Now, the GUI interface was invented back in the 70s and 80s by Xerox Palo Alto Research Center, Park Place as it's called. And they pioneered all of these graphical ways of doing computing. And it was actually Steve Jobs who saw this and said, that's a great idea. We should have this on our personal computer. And so that personal computer was the Lisa, which was the precursor to the Mac. Okay, the Macintosh. And the Macintosh was the Apple's graphical computer, and that has stuck even to today. So the early Apple computers were not graphical; they were command line interface driven. Okay. So we also have many other types of systems. Microsoft Windows uses graphical user interface, or GUI. It does have command line interface capability. You can bring up a command line window on Microsoft Windows. Apple's Mac OS, it has a graphical user interface, but underneath it uses a variant of the BSD Unix kernel, and you have available command line interfaces called shells. And Linux, which you saw, Ubuntu, when I demonstrated the command line, has graphical desktops that you can install with WIMP interfaces, things like KDE, GNOME, and CDE. What you saw when I ran the Ubuntu command line interface, that desktop was a GNOME desktop. Okay, so touchscreens are also an increasingly popular type of interface. This is an iOS version of the operating system by Apple, and these touchscreens add this haptic display, right? You now have gestures. Instead of a mouse, you use your fingers, and based on how you interact physically with your fingers, you can shrink something or increase something by pinching, as it's called. You can swipe left, swipe right, swipe up, swipe down, and your mouse is now gone, but those gestures detected on the contact-sensitive screen is now how you navigate around and select and click. That's your pointer device. You also have virtual keyboards, as well as increasingly these voice commands like Siri for Apple iOS products. So here's an example of the Mac OS graphical user interface. Again, it's a WIMP interface, window icon menu pointer. Let's take a look at system calls. So we'll end there. Rather than continue here, we'll just end here, and we'll use the opportunity to talk about system calls to actually do more on the C programming. So we'll end early here, and we'll pick back up on Tuesday. Please make sure you are looking at the material before each day, but certainly a little bit with the C and some of the reading before class on Tuesday. Do not fall behind in the reading. This is a marathon, not a sprint. So please make sure you do a little bit every day. Have a great weekend, and I'll see you all on Tuesday. Stay healthy and stay safe.